All right, gentlemen, hope we are doing well. We are on to chapter 6-2, where we're going to be talking about exponential functions. Okay, exponential functions. All right, we'll get into it in a little bit, right? But by the end of this lesson, we'll be able to sketch graphs showing key features of exponential functions. We'll be able to write exponential functions using tables and graphs, and then we'll compare both linear and exponential functions and see the differences and see what's alike. So exponential functions. Here is the basic formula, basic equation for an exponential. All right, f of x, okay, your output, is equal to a times b to the power of x, or to the x power. A is the initial amount. B is the constant ratio. Okay, A is the initial amount times b, the constant ratio, raised to the x power. Okay, exponential function is the product of initial amount and a constant ratio raised to a power. Make sure, again, we have this equation written down. Okay, so the other function that we've talked about so far in the year was linear functions, right? Y is equal to mx plus b, y is equal to x, okay? Linear functions. Here, we're dealing with exponential functions. Why is it an exponential function? Well, simply, the input variable, right, is an exponent. Okay, all right. Important, right? We need to be able to differentiate between linear and exponential functions. How are we going to do this? All right, well, linear functions, all x and y values in a table would have what's called a common difference. Okay, we'll call it, let's have a common difference. Okay, they'll have as x is increasing by 1, y will be increasing by 2, all throughout the function. Whereas exponential functions, all right, all the y values are going to have a common ratio. And I'll explain that a little bit later. Okay, but common difference for linear functions, common ratio between my y values for exponential functions. Okay, one, as mentioned in the swab up, okay, we're going to need to be able to graph. Okay, graphing exponential functions. One way we're going to graph an exponential function without a calculator is by using a table. Okay, we've done this a little bit before, but we've never quite defined it. So, all right, defined the rules for it. So the rules for graphing using a table. All right, first off, create a table. Okay, then set your x values. You're going to determine your x values. You're going to set your x values up. When you set your x values up, you want to make sure you choose numbers that are easy to work with. Well, what do I mean by that? Well, you want to choose numbers that are smaller, right? And choose 0 if you can, right? 0 is an easy number to work with, okay? All right. If we choose larger numbers, that can create a little bit more work for us, okay? So if we choose easy numbers, all right, they can both be easy to help compute, all right, our y values, all right? And they can also be easy from a graphing standpoint as well. You set up your graphs, okay? When you determine your all right, so next you set up your x values. After that, determine your y values. When to determine your y values, just take each x value one time, right? Take each x value, substitute that into the equation, and simplify that down to get y. So do that for each and every x value. So you want to repeat that process over and over for as many x values as you set up. Okay, here's a little concept summary. All right, and important to copy this down, okay, because again, exponential functions, right? A times b to the x power. A is the initial amount, b, all right, is my constant ratio. All right, now when b is larger than 1, all right, versus b, all right, is less than 1, but not negative, all right, there are differences, all right, that these present. So if my b value is greater than 1, right, so a b value of 3, all right, you are going to have a graph that is going to be increasing from left to right at an exponential rate. if we have a b value between 0 and 1, less than 1, a fraction, a decimal, this here is going to be decreasing from left to right. Okay, if my growth rate, again here, my constant factor, constant ratio is larger than 1, it's going to be showing an exponential increase. If it's less than 1, all right, but not negative, it's going to be showing an exponential decrease. All right, and then you can see here how the tables work. All right, so again, exponential functions, right? And we talked about this. We have exponents involved. Okay, this is going to be a drastic change, whether this is a drastic increase or a drastic decrease. Think back to the Desmos activity we talked about with Avi and Benita, right? They're two different rules for paying their employees. Okay, that same concept is ringing true here, right? And every single time as X is increasing, all right, my F of X values, my Y values, my outputs are going to be increasing by 3 each time. Okay, so I'm taking 2 times 3, 6. 6 times 3, 18. I'm multiplying by 3 each and every time. Why by 3? Well, that's my constant ratio. All right, 2, you can think of 2 here, your initial amount. So your initial amount, not too different than your y-intercept. Okay, let's take a look at here, right? 81 is my initial amount, right? So that's going to be my y-intercept right here. 2/3 is my constant ratio, which means it's going to be decreasing each and every time. So here, if I multiply 81 by 2/3, right, a number less than 1, it's going to be showing a decrease to 54. And 2/3 of 54, 36. 2/3 of 36, 24, and so on and so forth. So you're going to be decreasing at a very rapid rate, an exponential rate. Again, so again, make sure we have this table copied down here. All right, some examples. Let's talk through some examples here. So what does the graph of 2 to the x power look like? 2 to the x power. Let's look at the table and both the graph here. 2 to the power of x. Right here, you set up a table. Set your x values, then determine your y values. Okay, and you can see here, right, a number larger than 1. Right, so you're going to have an exponential increase. Okay, so an exponential increase here. All right, 1, and this is important for us to keep in mind. All right, exponential functions very rarely going to have x-intercepts. Right? So it's never really going to cross this x-axis here. We'll have we'll have a y-intercept. Okay, and now if you think about it here, all right, your y, so you only have one value here, 2. So if you only see one number there, what that means is that your a value, your initial amount, would be 1, because it would be 1 times 2. Right, so 2 here is your constant ratio. Right, it's multiplying by 2 each and every time. Okay. Other characteristics, it would be continuous between and beyond the x value shown. So the domain is all real numbers, right? And any x value here could be a part of this. All right, and one other term you want to make sure you're familiar with is this term called asymptote. Okay, the function gets closer and closer to the x-axis, but never quite reaches it. When a function approaches a line in this manner, that is called an asymptote. Okay, the asymptote of f is y is equal to 0. So the range is anything greater than 0. So nothing, all right, it's never going to go below the x-axis, nothing below 0 on my y-axis. Another problem that we want to take a look at, and this comes from a graphing perspective. This is a word problem here. All right, network admin uses the function f of x is equal to 5 to the x power to model the number of computers a virus spreads after x hours. Okay, so make a table. First thing, make a table here. Set your x values. Again, numbers you can work with here, easy numbers to work with. And then for every x value, plug in that here for the exponent of x. Right. you determine the y values. You can see here again, exponential increase. Okay, and again, you can see in the graph here, this as well. Now this problem adds a little question to it. If there are, so you make the graph and then answer these questions. If there are 1,000 computers on the network, how many hours will it take for the virus to spread to the entire network? All right, so if you go here for 1,000, okay, all right, when y is 1,000, x is about 4.3. So you can use the graph to estimate your answer here. Right, you can use it to estimate your answer there. Okay, the next type of problem we're going to see here is when we have a table, and then from a table, we have to write the equation. So we need two things here. We need the initial amount, and then we need the constant ratio. So initial amount, constant ratio. Those are the two things that we need. Initial amount is pretty straightforward. It's the y value, the output value, or the f of x value, however you want to think of that, when x is 0. So here, it's 4. The next thing we need is our constant ratio. Our constant ratio can be found by simply taking each y value and dividing it by the preceding y value. So here, 12 divided by 4, 3. 36 divided by 12, 3. 108 divided by 36, 3. 324 divided by 108, 3. So that's what it means by constant ratio. Between every y value, if you divide the following y value by the preceding one, the one that comes before it, right, you should get a constant ratio all the way through. All right, so your b is 3. So it would be 4 times 3 to the x power. If you are trying to do this from a table, right, you want to come up with ordered pairs and do a similar concept. You can tell what the initial amount here is by seeing the y-intercept, so that'd be 128. You can see here that this is decreasing, right? So you know the constant ratio is going to be less than 1. Okay, and then by simply doing 128 divided by 64, 1/2. Apologies, 64 divided by 128, 1/2, 32 divided by 64, 1/2, 8 divided by 32, 1/2, so on. So your function would be here 128 times 1/2 to the x power. The last problem we're going to talk about here is comparing linear and exponential functions. So linear, all right, in exponential functions, all right, you have a table, all right, two different tables. All right, we need to determine which one is linear, which one is exponential. Okay, linear functions, I mentioned earlier, have a constant difference, common difference. Okay, we're looking for a constant ratio between x and y. So here, all right, as x increases by 1, y is pretty steadily increasing by 25. So that would be a common difference. Okay. Option B, all right, you see here 1 to 3 to 9 to 27. That's not a common difference, right? This is increased by 2. That's increased by 6. That's not a common difference. So then you think about, okay, from 3 to 1 would be, all right, you divide that by, that would be 3. From 9 to 3, 9 divided by 3 would be 3. 27 divided by 9 would be 3. 81 divided by 27 would be 3. And then you can see there that it's multiplying by 3 each and every y value. So that would be the constant ratio. All right, so option A, linear. Option B, exponential. Okay, so lastly, we're going to look at our practice problems. All right, so we're going to practice, all right, number 1. Okay, you're going to practice number 1, number 3, A, and then number 5. So we're going to be identifying the key features of the function f of x is equal to bx when b is 2 and b is 1/2. So look at the differences between when that b value is larger than 1 and that b value is less than 1. Okay, and for number 3a, determine whether those ordered pairs, from those ordered pairs, come up with and write a exponential function. And in number 5 here, we're going to graph that exponential function. All right, so work on these on your own without a calculator. All right, and then tune in to the rest of the video to see the answers. So number 1 here, right? So going back to number 1 here for a moment, the b was 2, all right, versus when the b was 1/2. When the b value is 2, the exponential increases as x increases, where if the b is 1/2, the exponential function decreases as x decreases. Both have the same y-intercept. They would both have the same y-intercept, all right, of 1. All right, the domain in the range would be same as well as the asymptote. All right, it would be all real numbers on the x, okay? Anything larger than 0 on the y-axis, the range. However, all right, the one difference, again, going back to our comparison here, when our b value is larger than 1, you're going to have this increase up here, right, exponential increase, where if the b is less than 1, it's going to have that exponential decrease. So those are the two main differences. All right, so for number 3, let's take a look. All right, so for number 3, all right, for the second one here, all right, we have, all right, so I took all these ordered pairs and put them in a table. Okay, so we need two things. We need our a value, we need our b value. My a value is my initial amount. My initial amount is my x value and my y value when x is 0. So here, 3. All right, so it's going to be 3. And just going to find my b value. How do you find your b value? Well, divide 12 by 3. Right, that would be 4. All right, 48 divided by 12. That would also be 4. 192 divided by 48. Also 4, and so on and so forth. So you can see here the constant ratio here is 4. So it would be 3 times 4 to the power of x. Right, and that would be my equation. Okay, number 5. All right, number 5 here. Right, we're graphing. So graphing, set up your table. This would be your table, x and y table. Set your x values with easy numbers you can work with. So I pick 0, 1, 2, and 3. And for every x value, this is the equation, every x value, plug that into the exponent and simplify. So when f is 0, when x is 0, y is 1. Anything to the power of 0 is equal to 1. Okay, so that would be my coordinate here. And fill in your table for the y values. When my x coordinate is 1, right, plug that in. 3 to the first power, that would be 3. When x is 2, 3 to the second power is 9. When x is 3, 3 to the third power, 27. So once you have your x values, then you want to go ahead to your graph, set your graph up, make sure you have enough values on your y-axis and your x-axis. You can see here I go to 30 because my largest y value is 27. I'm just going to plot each point. So 1. Right, 0, 1. Be right about here.
Good afternoon today. Here are your afternoon announcements.
Okay, so 0, 1 would be here. 1, 3 would be here. Our next point is 2, 9. Right there. And 3, 27. So 3, 27 right here. Go ahead and connect the points. Can you show this drastic increase right on both sides? And then you have your function. Okay. We'll go over this in class. Hope you guys are having a good day. Come to class with questions. All right, jot them down now. Hope you guys